So good afternoon, everybody. First of all, I want to thank you all for joining us this afternoon. And before I go through my introduction as well as my colleague, I want to provide some context to our talk today. So I'm Timmy Mbaya, and my colleague Amalaye Oyake will go over our presentation today. And providing you some context, we've been here walking around, and it's so amazing to see all the technologies around here revolving around the Internet of Things. But we also got to be exposed so much to technologies such as artificial intelligence, edge computing, and digital twins. And what really transpires from this is the commercial ecosystem that's really supporting these game-changing technologies, creating a positive feedback, spurring even more development of these game-changing technologies. And so today, as within this context, we're going to be talking, me and my colleague, about a low Earth orbit destination for industry transformation. We call it Orbital Reef, because it is in orbit in our space frontier, providing an infrastructure and a platform supporting these game-changing technologies. So I'm Timmy Mbaya, and I work with Blue Origin as an Avionics and software lead on Orbital Reef, and we have Amalaye Oyake, who is a senior flight software lead on Orbital Reef. And as I said, our goal is to provide this platform in the next space frontier, being part of this ecosystem supporting these game-changing technologies beyond Earth, but including in space, so that we can have millions of people living and working sustainably in space. Here you have an artistic rendering of the end game, essentially, where you can see a scalable space station with a lot of habitat. This is an inflatable habitat, and supporting vehicles. We'll go over some of these components and how they support the ecosystem for these game-changing technologies. And as I said, we work as an enterprise with several partners, bringing in several levels of expertise to support this ecosystem and the platform that will advance the growth of the Internet of Things, including edge computing and more in space. Now, here we have a small video that will articulate our vision before we go on in describing some of the details. So this short video actually captures it very well. As it states at the end, it's about being able to have your address in space. There are three elements here to remember. Pioneering, so we can support research, not just national research, but industrial, commercial industrial research, creating for commercial production, and just living in space in order to promote millions of people living and working in space as we develop an infrastructure to support these game-changing technologies beyond Earth, but in low Earth orbit as well. So this is what we are working on with our main partner, Sierra Nevada, developing this low Earth orbit destination to advance industry transformation, leveraging these game-changing technologies. The goal, again, is to build a road to space. To build this road, we need to be part of the ecosystem with the Internet of Things, digital twins, edge computing, and many more. As you can see, walking down the floor here, we learned so much about sensing technologies, robotics, and all these are interconnected, providing an ecosystem. And if we want to further it to the next frontier, we need the infrastructure starting in low Earth orbit as part of our road together to space. But to get there, we need some enabling technologies. Just like here, the New Glenn orbital rocket. We're not going to get into a lot of details on this because our focus is on Orbital Reef, but this is an enabling technology that will help us provide transportation to low Earth orbit with enough fairing. As you can see, the payload fairing is big enough, 7 meters, to provide enough cargo for enough space for crew and cargo. And the other aspect is a reusable first stage to lower the cost of access to space. And this is the typical mission profile from liftoff, ascent, stage separation, and landing of the first stage. This is critical, talking about our low Earth orbit destination for industry transformation, because part of it is lowering the cost of access to space. Some other enabling technologies would be the vehicle system, the visiting vehicles that will bring cargo or crew to space. You're probably familiar with this on the news. We have like the Dream Chaser that will also start supplying the International Space Station. We have the Starliner, which flew to the space station last year and has a crewed flight scheduled for sometime this year. And all these enabling technologies essentially will provide support for the Orbital Reef space station so that it can be supplied, so it can be crewed, and so it can be safe for the astronauts and the crew on board the station. We are familiar with the International Space Station and how much it has served us. We've learned a lot from the International Space Station that was developed. I mean, it has been around for more than 25 years, and its development started actually more than 30 years ago. And now we are moving to the next phase by developing a commercial space station, which will be commercially developed, owned, and operated. Because the next step now is for a commercial space station that with an open and scalable architecture in order to promote these game-changing technologies further and be part of this positive feedback loop, but also beyond Earth and in low Earth orbit, as part of our road to space, to have millions of people living and working in space. So here we have some of the different configurations of this space station. As I said, one goal is to be scalable. So the base configuration is represented here. The big module here is an inflatable habitat, where most of the habitat for the crew astronauts will be. And then we have a node module here, Altis developed by partner Sierra Space. Then we have the connecting core, I would say, the core, which is between the different modules so that astronauts and crew can move from one module to the other. And you can see some big windows. As the design is not to be cramped, but in order to be livable and to accommodate all these emerging technologies that we are used to here on Earth. And you can see some visiting vehicles providing either cargo or crew, and a research module. And the next one here is a representation of a scaled or expanded configuration, where by adding more cores, we can add more modules as the station expands and scales to further needs. So here in more details, you can see like a power and propulsion module with some solar arrays and radiators and just a core. So even in this very basic configuration, we can already provide some of the services supporting all these technologies just on the core before more module comes and connects to the space station. Because in the end, it will be about providing end-to-end services for research, commercial industry, with accommodation for the crew and the needed support for the crew and the different technologies. Some further details here of the different modules of the station. So we have the energy mast here, essentially responsible for power and propulsion. We have a research module providing national and commercial industry research as well. The habitat, the expandable habitat here, and a node module that also supports extravehicular activities. And as stated earlier, we have some supporting technologies, including a reusable rocket and visiting vehicles. So the goal really is to go beyond, say, the International Space Station and open the doors to new markets in low Earth orbit, supporting not just national research, but the commercial industry as well, including production, and supporting not just exploration services, but as well as consumer productions in space, and not just supporting in-orbit support of satellites, but as well as travel and tourism for millions of people living and working in space eventually. Here we have a cutout representation of the station, showing some details of what it looks like inside and what is supported. So in the center here, we have the core module right in the center with the energy mast. And as you can see, it's very spacious, providing some accommodations for equipment, for work, as well as for the crew to move between modules. On the right here, you have the research module. In yellow there, you can see some intravehicular robotics standing to the mid-locker equipment for research. And as I said, this will be not just for national research, but commercial production and research as well. On the left here, you have the inflatable life module, where most of the crew quarters would be, including environmental control and life support systems. And we have a node here supporting extravehicular activities when the astronaut needs to get out of the station. An artistic rendering of what it would look like inside. As you can see again, the design is modern. The design goes beyond just people doing research. The design is there to accommodate the different types of activities that will be supported by the station. You can see large windows. And at the bottom, we can have some private areas or work areas. Astronauts can move freely around. And as you can see, it is designed to be open and scalable to support different technologies, such as, for instance, these giant flat screen displays that are part of our ecosystem right now. Here is a rendering of the life module, the inflatable habitat. And you can see the Astro Garden here, the artistic rendering of the Astro Garden. Most of the crew quarters would be in this life inflatable habitat. Here is a rendering of the research module. And again, as you can see, very spacious and designed to accommodate these game-changing and emerging technologies. And now my colleague Amalaye Oyake will go over some of the technologies that are out there already being supported by low Earth orbit platforms.
Thank you, Timmy.
Sure.
I'm just going to do a mic check to see if my audio is working. Can everybody hear me? Is my audio? Okay, perfect, great. So thank you, Timmy, for giving just a great presentation on Orbital Reef. And it's really a treat because Timmy is actually the flight software lead on the Orbital Reef space station. So I work under Timmy. And what I'm going to do right now is talk about the Internet of Space. So this is the IoT conference. We're talking about the Internet of Things. How do machines communicate with other machines? There are other considerations and things that we're concerned about, such as security. How can we make sure that our communication is secure? So you may not already be aware, but the space station has an internet connection to the ground. It has a very solid internet connection to the ground, and internet services already provided on the ISS. Some of the standard services that exist on the space station are real-time telemetry downlink, real-time video downlink, the replay of telemetry, health and status telemetry, but then there are internet services provided via the space-to-ground link, such as file services, TCP and UDP services, and highlighted in yellow at the very bottom, DTN, disruption-tolerant networking. So what is disruption-tolerant networking? Disruption-tolerant networking, or colloquially called space internet, is a suite of protocols that was developed by NASA in collaboration with Vint Cerf at Google to build a set of protocols that can support communications over long distances or in scenarios where you might have intermittent or extensive connections. So I'm going to point this. And I talked a little bit about this. The standards exist and are documented in several documents. So if you're very interested in IETF documents, these are some of the RFCs that you can read. RFC 4838, 5050, and lots of others that describe the bundle protocol, the Licklider transport protocol, and also several CCSDS blue books. So what is CCSDS? We are at the IoT conference. We are trying to get things to talk to one another. They're standards bodies that define data communication in the space domain. So the OMG is very active in the space domain with the OMG Space Domain Task Force. So they've defined standards such as the XTCE telemetry standard. And then there's also the CCSDS, which defines packet protocols for communicating in space. Okay, there are several open source implementations of the disruption-tolerant networking protocols. One is called ION, and there are several others from academic sources as well. The DTN protocols are a standard service for users on the International Space Station. So if you have a payload and you want to send your data back down to the ground, you don't have to worry about replaying the data if you miss your communication link. These protocols handle all of that for you. There's going to be a short video coming up where the DTN protocol will be described in detail.
Working as
And
part
here
of
it
a
is.
NASA-wide team, engineers from the Jet Propulsion Laboratory in Pasadena, California, have used software called Disruption Tolerant Networking, or DTN, to transmit dozens of space images to and from NASA's Epoxy spacecraft, located more than 20 million miles from Earth. To develop this new technology, NASA partnered about 10 years ago with Vint Cerf, a vice president at Google and co-inventor of the TCP/IP protocol used in the terrestrial internet.
In simple terms, it's like creating an internet in space that's like the internet terrestrially, but it has some different characteristics. Things are a lot farther apart in space. The distances between the planets are literally astronomical. And so the delays at the speed of light are very high compared to what they are on the ground. So the methods that we use for the terrestrial internet don't quite work when we're going at interplanetary distances, and we've concluded after quite a bit of work that we needed to design a new set of communication protocols.
DTN does not assume a continuous end-to-end connection. In its design, if a destination path can't be found, the data packets are not discarded. Instead, each network node keeps custody of the information as long as necessary, until it can safely communicate with another node. This store and forward method enables reliable delivery of information to the end user while tolerating disruptions in communication.
If you're doing space communications and you have something sitting on the surface of a planet and the planet's rotating, you can't talk to it until it comes back around again. And some satellites may behave the same way. You may not be able to see them to talk to them. So the communication in this deep space network becomes disrupted, and similar things happen terrestrially under some conditions. So the delay-tolerant networking is designed around the idea that things are not always connected, that you should not be expecting a response to come back right away. In fact, you're not even sure when it will come back. So you build your system to be very, very tolerant of an uncertain amount of delay and frequent disruption of communication.
Engineers began the month-long series of DTN demonstrations in October, using the Epoxy spacecraft as a simulated Mars relay orbiter. The DTN software ran continuously on board the spacecraft for 30 days, and data was transmitted using NASA's Deep Space Network twice per week over this period.
So what we're simulating here this morning is a probe on, say, a rover on Phobos. We just picked a name, a rover on Phobos, sending data to a lander on Mars via several hops of relays.
All right, all stations, we have confirmation. The experiment data has been received. Flight copy. Congratulations.
This experiment was the first in a series of planned demonstrations to qualify the technology for use on a variety of upcoming missions. In the next few years, interplanetary networking could enable new types of exploration. Complex missions involving multiple landed, mobile, and orbiting spacecraft will be far easier to support through the use of the DTN.
Well, the general public probably doesn't pay a lot of attention to the details of infrastructure. They don't think about the Deep Space Network or about the protocols of the internet. They just use it. And so I think if they could be excited about this at all, it will be because we will be enabling more scientific information to come back from much more complex experiments, learning more and more about the solar system and its origins and its ultimate destination. Maybe a lot more about whether life could exist in the solar system or whether it ever has existed. And even using spacecraft to look further and further out into the universe to understand more about its origins. So they should be excited about this because it's enabling our scientists to do more than they ever did before with space-based exploration.
So I'm going to try and get this laser pointer working. So I talked a bit about DTN, and you got to see the video of Vint Cerf describing the DTN protocol. As I shared earlier, the DTN service is a standard service already running on the International Space Station. So payload developers are able to leverage this protocol to increase their science data return from their experiments. They no longer have to worry about manually retransmitting their data from space when they lose communication. The protocol automatically handles this. So what FinSurf said at the end is that if we can take anything away, we need to be excited about protocols that enable more data return in the presence of disruption or noise or disconnection. And so I'm going to talk a little bit more about the DTN protocols. The relation to Orbital Reef is that Orbital Reef, at a minimum, will provide the already existing services that exist on the International Space Station. And this is but one of them. But in the context of this conference, this is the most exciting protocol that we need to understand and learn about. So if you're trying to do machine-to-machine communication and you're trying to solve the problem of remote sensors in remote places and things that are being disconnected, you need to understand the protocols that already exist, that already have open source implementations, and that you can use for your experiments. So part of the DTL protocol stack is LTP. So LTP is, in essence, what we call TCP for space. It's the Licklider transmission protocol, named after JCR Licklider, one of the pioneers of the internet. And if you can see here, it describes the protocol. It supports extremely long round-trip message times. And this type of communication is common in interplanetary space, but it's also common among sensor networks in very remote scenarios. The stack itself is built up as follows. So you have your typical 7-layer ISO stack. You have your applications and your types of messaging, message styles. You might have publish and subscribe. There's an AMS service. It's called the asynchronous message service. You have a file delivery service. It's called CFDP. These are standard services that already exist in open source and are used in the space domain. The data flows down the protocol stack and is encapsulated in an envelope called a bundle. So a bundle is essentially a very large packet that is transported in a store and forward mechanism. That bundle flows through the lower stacks through a convergence layer and is passed to the Licklider transportation protocol. So what happens in LTP is that the bundles are chopped up into smaller segments and flowed across the link layer. So what LTP does is make sure that the bundles can flow across the radio link, particularly the radio FIFO. So your radios have a FIFO, and that's one of the constraints of space communication. So you can read more. There's a paper here called The Internet of Space that describes this a lot more. So with Orbital Reef, we've already had some customers, and we had something called the Orbital Reef Starter Innovation Challenge. And we had 4 winners, and these are some of the winners. Prometheus Life Technologies, which was looking at human tissues development in microgravity. Lunasonde, which was looking at signal attenuation. And then there was another company called EcoAtoms, which is developing biosensors in space. And the last one was Fluix, which is looking at nano-suspension cooling technologies and developing those in space. So at this early stage, we already have industries lining up and looking at how they can do experiments or develop products in the space environment. So Orbital Reef is an active development. As I shared, Timmy is the flight software lead. I'm working under him. There's a lot of active work going on, but we want to share about this project and the difference between Orbital Reef and the ISS. The Orbital Reef will open up space for the commercial, for the commercial sector. From a Blue Origin perspective, we've already sent 30 people to space. So last year we sent 30 people to space, including 3 employees. And so as we move forward, we expect to continue that trend, and as we build our capability, we expect to send more and more people to space. And hopefully, as we develop Orbital Reef, we will begin to send people to low Earth orbit. Thank you very much.
Well, thank you for joining us and allowing us to share with you our work on Orbital Reef. And we hope that this presentation has shown you how we can leverage this platform together as we build our road to space for millions of people living and working in space, leveraging all these game-changing technologies that we all here are working on and enthusiastic about. Thank you.
And we have an Orbital Reef website that provides a lot of background information on the project. And you can look at that, as well as the Blue Origin website that also provides a lot of details. If there are any media requests, we have a media team that can respond to those directly. So thank you very much.
Thank you.